It's 2:47 in the morning. A disk controller dies in a server rack you've never physically seen. The app it was running just stops. Nothing notices. No alarm, no failover, just a service that's down quietly. Until a customer complains and a pager drags a human out of bed to rebuild a machine from memory. Now here's the part that should scare you. At real scale, this isn't a rare disaster. In a large cluster's first year, you can expect on the order of 1,000 machines to fail. A human reacting to each dead box one at a time is not hard, it's mathematically impossible. So the entire industry needed a system that treats failure as normal, that keeps your apps running without a person in the loop. That system is Kubernetes. And the reason it still wins, even now, in the age of billion-dollar AI clusters, isn't hype. It's that the problem it solves never went away. Let's build the whole thing up from scratch, from the pain that created it, so you can see why every piece has to exist. To understand the answer, you have to feel the problem, so let's do it by hand. Start simple, one app, one server. A request comes in, a response goes out. This works. Traffic grows, and to save money, you drop a second app onto the same box. But now, under load, the two apps fight over the same CPU and memory. There's no wall between them, no resource boundary, so the analytics job eats all the RAM and checkout slows to a crawl. Fine, you split them onto two servers. But now you've created snowflakes. One server was set up in March by one person, with one version of a library and a hand-edited config. Another was set up in July by someone else, with different versions. A deploy that works perfectly on one server silently fails on the other. Configuration drift, and nobody wrote down the changes. To ship a release, you SSH into each box and run commands by hand. 3 boxes is annoying. 30 is a full-time job. One fat-fingered step and production is down. And the worst case, 3 in the morning, a box dies, and because it's a snowflake you can't quickly reproduce, you rebuild it slowly from tribal knowledge. Every one of these is a different symptom of the same disease. You're performing operations by hand that the number of machines has already outgrown. Now the hardware world wasn't standing still, but watch which problem it was actually solving. Era 1, bare metal. Apps sit directly on physical servers with no way to draw resource boundaries, so one app can starve the rest. The obvious fix, one app per server, doesn't scale, because most of that hardware sits idle and it's expensive. Era 2, virtual machines. You slice one physical server into many VMs, each isolated, each improving utilization. But every VM carries a full operating system of its own. It's a whole machine, so it's heavy, slow to boot, wasteful. Era 3, containers. Like a VM but with relaxed isolation, so all the containers share the host's operating system. That makes them lightweight, portable, and, crucially, reproducible. The same image runs on your laptop exactly as it runs in the cloud. So containers finally solved packaging. They gave us a clean, identical unit to ship. But this is the hinge of the entire story. A container by itself still doesn't decide where to run, won't restart itself when it dies, and won't move its work off a failed machine. The packaging problem is solved. The operations problem is not. So look at what's left. Everything the human was doing by hand, place the app on a healthy machine, keep every machine's config identical, notice the moment one dies, and move the work somewhere else. None of that is solved by a nicer box. That surviving gap has a name, orchestration. And it's not a new invention. Inside Google, a system called Borg did exactly this job, placing, packing, and healing every workload across tens of thousands of machines for over a decade. Kubernetes is those hard-won lessons, packaged so the rest of the world can benefit. So let's earn every piece of it. And it all rests on a single idea. Here's the single idea the whole system is built on. Stop giving commands. Start declaring intent. A command acts at one instant and then it's gone. You typed start 3 copies on Monday, and that action evaporated the moment it finished. So when a machine dies at 3 in the morning and you silently drop to 2, nothing brings you back, because 3 was never written down anywhere to compare against. Kubernetes inverts this. You record your intent as desired state, I want 3 durably, and then a program runs forever doing 3 things in a loop. Observe the actual world, compare it to your desired state, and act to close the gap. Let's run it by hand. You hold a sticky note, I want 3 web servers. You look at the cluster, 3 running, actual equals desired, so you do nothing. 10 seconds later, you look again. Still 3. Do nothing. That's the loop, observe, compare, act, repeat forever. Now a node dies. You look 2. Compare to the note, gap of 1. You act, start 1 more. Back to 3. And notice nobody had to tell you the node died. You discovered it just by looking at reality and comparing it to your intent. This is the thermostat in the Kubernetes doc's own words. You set the desired temperature, the room's actual temperature is the current state, and the furnace clicks on and off to close the gap. Self-healing isn't a special feature bolted on. It falls out of this loop for free. This loop is the spine of everything that follows. There's a subtle trap here, and it's worth 30 seconds because it explains why Kubernetes is so hard to knock over. Imagine you make yourself event-driven instead. You only act when someone shouts a node died. Now the node dies while you're on a coffee break, your process restarted, you missed the shout, nobody repeats it. You come back, you never heard it, so you do nothing. The cluster stays broken forever. That's edge-triggered, you react to the event, and if you miss the event, the correction is lost. Kubernetes refuses to work this way. Its loops are level-triggered. They don't trust their memory of events at all. They just reread the entire actual world right now and compare it to what you declared, regardless of what happened or what they missed. Miss an event. The next pass catches it anyway. That's why a dropped message, a network blip, or a controller restarting mid-crash all self-correct instead of becoming permanent damage. And it's why the design is many small, independent loops rather than one giant brain. A loop can fail, so the system is built to let it fail and be restarted without taking everything down with it. Now we can build components and the rule from here on. Every piece is introduced by the problem it solves. First problem. A container isolates a single process. But sometimes 2 processes are a team that must live together. Say a web app that writes logs to a file, and a little helper that reads those logs and ships them off. Try to run them as 2 bare containers and be the scheduler by hand. You place the web app on node 1. You place the log shipper next, but nothing says it belongs with the app, so you drop it on node 2, which had free CPU. Immediately dead. The shipper opens the log file on node 2 and it's empty. The logs are on node 1. Okay, force them both onto node 1. Better, but now the app exposes a metrics port on localhost, and the shipper tries to reach localhost and gets connection refused, because each container has its own localhost, its own network sandbox. Same machine, separate worlds. So Kubernetes was designed to give you back the same machine guarantees as one unit, the pod. A pod is one or more tightly coupled containers that are always placed together, on one node as a single atom. Kubernetes quietly starts a tiny pause container first that creates and holds one shared network space. So both your containers get the same IP, the same localhost, and can share a volume for those log files. Place them as one, move them as one, replace them as one. Every failure you just watched disappears, because you stopped scheduling loose processes and started scheduling the group. Next problem. A real application isn't one pod. It's many identical copies that must all stay alive on machines that fail randomly, while you also ship new versions without going dark. The naive answer is, a human or a startup script launches many copies and watches them. But that's a command. It captures an action at one instant, not a standing truth. So watch it break. You start 3 copies of your API by hand. Tuesday 3 in the morning, the kernel kills copy number 2. Nothing restarts it. Your launch command finished running on Monday. You're at 2/3 capacity, and the first thing that tells you is a latency alert or a customer. Now hand it to Kubernetes. A ReplicaSet is a loop whose whole job is keep a stable number of pods matching this template running at all times. It knows which pods count toward the target by a label selector, like a magnet that only attracts the matching ones. Kill a pod, the count drops. The loop notices the gap and creates a replacement. That's the spine again, desired versus actual, applied to a count. Now the harder half, shipping version 2. If you stop all the V1 pods first to swap them, there's a window where 0 are running downtime, and if V2 crash loops on a bad config, you've already killed V1 and have nothing to fall back to. So a deployment wraps the ReplicaSet to change desired state safely over time. It stands up a new ReplicaSet for V2 and moves the two counts in opposite directions a little at a time. V2 scales up while V1 scales down, a little at a time in lockstep, governed by how many extra you may run and how few you may drop below target. The running total never dips below what you need. And the old V1 ReplicaSet isn't deleted, it's scaled to 0 and parked as a saved snapshot, so a rollback is just scaling it back up. A bad deploy becomes a non-event instead of an outage. Now those pods need to talk to each other, and here's the catch. Every pod gets its own IP, but a pod is ephemeral. It crashes, it reschedules onto another node, it scales up and down, it rolls during a deploy, and every replacement comes back with a brand new IP. So do it naively. Your front-end hardcodes a back-end pod's IP 10. something. It works until that pod reschedules and comes back at a different address. Now the old IP points at nothing, connection refused, or worse, at a different pod that recycled that address. So your requests silently hit the wrong workload with no error at all. And even if you kept up, hardcoding one IP gives you no load balancing. One replica melts while the others sit idle. You're chasing a moving target. So Kubernetes was designed to give you the one thing that doesn't move: a service. A service gets a stable virtual IP and a stable DNS name, and it continuously maintains the mapping from that fixed front to the shifting set of healthy backend pods behind it, tracked in a live list called endpoint slices. Your frontend doesn't ask where is the backend, and write down an address, it just connects to the name backend, which resolves to that one stable virtual IP, and the traffic is automatically spread across whatever replicas are alive right now. A pod reschedules. The list quietly swaps the dead IP for the new one. Your connection to the service is untouched. A pod dies. It's dropped from the list, so nothing gets routed to the corpse. You changed nothing. The moving target problem simply evaporates because the thing you address stopped moving. Google's Borg learned this same lesson years earlier. Tasks move, so you address them by a stable name, never by raw location. The service solved talking inside the cluster, service to service, what network people call east-west traffic. But now you want to expose things to the outside world, north-south traffic, in and out of the cluster, and that's a different problem at a different layer. A service works at layer 4. It routes on IP and port, and it is completely blind above that. It cannot read a web request's hostname or its URL path. So try the naive thing. Expose each microservice with its own external load balancer. 15 services becomes 15 cloud load balancers, 15 public IPs to wire into DNS, and 15 separate TLS certificates to install and renew. Your bill scales with your service count, and the day a cert quietly expires on service number 9, that's a silent outage. Worse, you physically cannot send shop.com/API to one service and shop.com/blog to another, because layer 4 never opens the request to read the path. So Kubernetes adds a single, stable layer 7 front door, Ingress. One external entry point that terminates TLS once, then reads the hostname and the path of each request and routes it to the right internal service. One load balancer, one IP, one certificate, and real routing. This host goes here, that path goes there, everything else to the storefront. Ingress doesn't replace services, it sits in front of them and points at them. And one honest catch, writing the Ingress rule does nothing on its own. It's just a statement of intent. You need an Ingress controller running to actually fulfill it, the same declarative pattern as everything else. You declare what you want, and a loop makes it real. Everything so far quietly assumed your pods are interchangeable. Any copy is as good as any other. Databases are the exact opposite. Each member owns its own durable data, needs a fixed address its peers can find, and must start and stop in a defined order. Run a 3-node database as an ordinary deployment, and 3 things break almost instantly. 1. Storage. A typical network disk can be mounted read-write by only one node at a time, so your extra replicas get stuck, unable to attach. And if you force them to share one disk, multiple database engines scribble over the same files and shred the data. Each node needs its own disk that follows it. 2. Identity. The deployment gives pods random names and fresh IPs on every restart. So a member you were replicating from crashes and comes back as a total stranger. Its peers are now talking to a ghost. Each node needs a stable name that reattaches after a reschedule. 3. Order. A replica can only sync after the primary exists, and a rolling update that restarts 2 of 3 nodes at once can destroy your majority. Writes freeze, or 2 nodes both think they're the leader, and the data diverges. So Kubernetes was designed for this with the StatefulSet, and it makes 3 things sticky to each pod for its entire life. A stable ordinal identity. The pods are named 0, 1, 2, not random hashes. A stable per pod volume. Pod 0 always reattaches to volume 0, even if it moves to another machine. And a stable order. Pods come up one at a time, each waiting until the one before it is ready. And updates walk the members one by one so the majority is never broken. One honest boundary. The StatefulSet gives you identity, storage, and ordering. It does not do the replication or leader election for you. That's still the application's job. Kubernetes guarantees that Node 1 keeps being Node 1 with its own data and its own name. Deciding who's the primary is up to your database. Step back and notice something we've quietly relied on this whole time. When a pod on one machine talks to a pod on another, it just uses the other pod's IP directly, as if they were on the same flat network. That's a deliberate design choice, and it's worth seeing the alternative to appreciate it. The naive way is per node address translation. Every machine hands out its own private IPs and rewrites addresses at its boundary. Now a pod's address means different things depending on where you're standing, ports collide, and you spend your life mapping and remapping. Networking becomes a maze that every other feature would have to navigate. So Kubernetes demands a simpler model. One flat network where every pod gets a genuinely unique IP and can reach every other pod directly, no translation in between. This is the foundation the service layer stands on. A stable virtual IP can only forward to a real pod IP if that pod IP is reachable from anywhere in the cluster in the first place. Get the flat network right, and everything above it, services, DNS, Ingress, becomes clean. Now the money question. You pay for whole machines whether they're busy or idle, so the only real lever on cost is running the same work on fewer of them. Be the scheduler by hand, 3 servers, 8 CPU cores each, and 6 services that each need 3 cores. Play it safe and spread, 1 service per server, then a second round, and every server ends up at 3/4 full with idle cores scattered across all 3. All 3 machines lit up, all 3 bills running. Now pack instead. Fill the first 2 servers and the idle capacity concentrates into the 3rd server, whole and empty, so you turn it off and stop paying for it. That empty machine is the entire point. Packing gathers your waste into whole machines you can delete. But packing has 2 dangers, and Kubernetes answers both with 2 different numbers. First danger: if you pack based on what apps are using right now, you'll pile work onto a node that looks empty only because everything's briefly idle. Then traffic hits, everyone wakes up at once, and the node is catastrophically oversubscribed. So the scheduler packs against a declared request, a reservation, a booking, never live usage. You can't sell the same seat twice. Second danger: once you pack neighbors tightly, one buggy app could eat the whole machine. So each container also declares a limit, a ceiling the kernel enforces, and here's a subtlety worth knowing. Over your CPU limit, you get throttled, slowed down. Over your memory limit, you get killed because you can't slow down bytes that are already written. That ceiling is what makes dense packing safe, which lets you pack tighter still. Now the punchline: Kubernetes doesn't even do this aggressively by default, it spreads. And real-world fleets show why it matters. Across tens of thousands of production clusters, average CPU utilization sits around 8%. Most of the machines the world is paying for are doing almost nothing. Google proved the payoff long ago with Borg segregating workloads onto dedicated machines instead of packing them together. Needed 20 to 30% more machines. Packing isn't a nice-to-have. It's the whole economic argument. We touched rolling updates earlier. Now let's make the no downtime claim honest, because the rolling replacement alone isn't enough. Picture the naive upgrade one more time. Kill the old, start the new. Even done gradually, there's a gap. The new pod's process has started but isn't actually ready to serve yet. It's still loading, still connecting to its database. If traffic gets routed to it in that window, users hit errors. So Kubernetes adds health gates, a readiness check that a pod must pass before the service will send it any traffic at all, and a liveness check that restarts a pod that is wedged. Now the rolling update has a rule it can trust. Don't route to a new pod until it says I'm ready, and don't remove an old pod until its replacement is truly serving. Layer on a graceful shutdown so in-flight requests finish, and a budget that caps how many pods can be down at once even during node maintenance, and the running fleet never dips below what it needs. That's the honest framing. Kubernetes doesn't guarantee zero downtime by magic. It gives you the health gates and the controlled replacement rate that enable it if you wire the checks up correctly. So why does all of this matter more in the age of AI, not less? Because AI turned the utilization problem from expensive into brutal. GPUs are scarce and cost real money per hour, and an AI org runs two very different kinds of work at once. Big interruptible training batches and always-on, latency-sensitive inference. Give each its own fixed pool of GPUs, and you strand idle silicon on both sides. So you want them sharing one pool, which is exactly the packing problem from a minute ago, just with far more expensive bins. Be the scheduler again. Plain Kubernetes only understands CPU and memory. It can't even see a GPU. So it double books one card and the second job dies with an out-of-memory error, even though the CPU had room. The fix is a device plugin that advertises each GPU as a countable resource. So the scheduler treats a GPU as a token it can hand out exactly once. But now the next trap. A whole GPU is one indivisible token, so a tiny inference service that uses 10% of a card still claims the whole card, and a big training job waits, while 90% of your most expensive hardware sits idle behind it. So you enable GPU sharing, hardware partitioning a card into isolated slices, or time slicing between pods, to fit several small jobs on one card and free whole GPUs for training. And at 2 in the morning when traffic drops and inference scales towards zero, an auto-scaler deletes the now empty GPU machines so you stop paying, and recreates them when demand returns. Look at what you just rederived by hand. Count the GPUs, pack and share them, and hand back the ones you're not using. Those are the exact 3 moves, and they're not new. This is Google's Borg, which for over a decade ran latency-sensitive services and batched jobs together on shared clusters of tens of thousands of machines, packing them densely, treating failure as normal. Kubernetes is Borg's open-source descendant. AI didn't invent a new infrastructure problem. It put a much bigger price tag on the old one, and handed it to the system that was already built to solve it. We've talked about Kubernetes as if it's one brain. It isn't, and the reason it's split apart is the same reasoning we've used all along. Imagine you did build it as one program. It holds the cluster's state in memory, decides where things go, and directly launches containers. Watch it fail. It tells a node to run a pod, then crashes before recording that it did, reboots with amnesia, and schedules the same pod again somewhere else. Now you've got duplicates and split brain. The only safe way to recover from any crash is to keep exactly one durable source of truth, write every decision to it before acting, and make everything else a stateless loop that can die, restart, reread that truth, and continue. So Kubernetes separates storing from deciding from acting. Let's build it by hand. You write your intent on a whiteboard. I want 3 servers. That whiteboard, the durable source of truth, is etc. Nobody scribbles on it directly. Everyone goes through one gatekeeper that validates every change and is the only writer. That's the API server, the single front door. A placement helper reads the board, picks which machine each server goes on, and writes the assignment back. That's the scheduler. Notice it decides but doesn't launch anything. On each machine, a worker reads the board, sees a server assigned to it, and actually starts it. That's the kubelet, which makes reality match. And the reconciliation loops we've leaned on this whole time, the ones comparing desired to actual, that's the controller manager. Now kill the front door process. Because the truth lives in the durable store and not in anyone's head, it reboots, rereads the board, and the cluster just continues. No amnesia, no duplicates. And when two loops try to change the same thing at once, the writer with the stale version is rejected and simply retries, so updates are never silently lost. Storing is not deciding, is not acting, and that separation is exactly why no single failure can corrupt the whole. So here's the whole thing in one breath. Machines fail constantly, and a human can't be the failover. So you stop giving commands and start declaring the state you want, and tireless loops drive reality toward it forever. The pod exists because tightly coupled processes need one shared home. The deployment because many copies must survive random death and roll to new versions without a gap. The service and its DNS because pods move and you can't chase a moving address. Ingress because the outside world needs one smart front door. The StatefulSet because databases need identity and order. The flat network so all of it can even reach each other. Bin packing because idle machines are just money on fire. And the split apart control plane so no single crash can corrupt the truth. Not a checklist of nouns, one idea applied everywhere. And that's why Kubernetes stays the answer in the age of AI. AI didn't retire this problem. It bought the most expensive hardware in the industry and made packing it, healing it, and declaring it once matter more than it ever has. The problem that created Kubernetes didn't go away. It just got a much bigger price tag, handed to the system that was built from the very beginning to pay it.